Okay, so there are a few types of energy, but if you want to know in detail, including how to calculate the energy amounts. So the first one we're going to look at is kinetic energy. Kinetic energy is all to do with something is moving. So when you have something that's moving, it has a store of kinetic energy. And the equation for kinetic energy is as follows, that kinetic energy, or KE, is equal to half multiplied by the mass multiplied by velocity squared. And so we're going to label these on. So this is your kinetic energy, you already know, so we won't bother labeling that. This is your mass, and over here is your speed or velocity squared. And so we'll put some units on as well. And so the units for mass is kilograms, the units for speed is meters per second, and the units for kinetic energy then is usually given joules like that. And that is the amount of energy, or if you are to calculate kinetic energy, then that is how you would do it. You would use that formula there. The next type of energy which we want to know in detail is elastic potential energy. So let's take that over here. And don't worry, we'll give you guys a chance to practice these at the end of the video. So do watch till the end. So the elastic potential energy is all to do with when you have essentially a spring that's being stretched. So it might not necessarily be a spring, but anything that can be stretched or compressed has some form of elastic potential energy. Okay. And once again, we want to know the formula. So EPE, elastic potential energy, is equal to a half multiplied by K multiplied by E squared. And if you want to know this formula in detail, what each of these mean in detail, then do go ahead and watch the video we've done on compressing and stretching materials. Essentially, let's once again label these. So K is actually your spring constant. And this basically tells you how stiff a spring is. So this will usually be given to you. E is your extension. So how far you're extending your spring. And once again, we can put some units on. So the spring constant is usually given in newtons per meter. The extension is measured in meters, and EP once again is usually joules. Okay, so don't worry if this doesn't make too much sense. Like I said, if you want to know a bit more about this equation, you can watch the video we've done on Hooke's law and springs in general. The next thing we want to look at then is gravitational potential energy. So this is one that, much like kinetic energy, we looked at in the previous video. So gravitational potential energy is all to do with when you raise something up a height. So whenever anything has a certain height or is raised up above a certain height, then it does have a store of gravitational potential energy. And once again, we can write the equation out. So GPE is equal to a mass multiplied by gravitational field strength multiplied by H. So this is mass. This is your gravitational field strength, which is usually 9.8 on Earth. And this is your height. And once again, we'll put some units on. And so mass, once again, is going to be in kilograms. G is your gravitational field strength. And generally, this is in newtons per kilogram. And your height will be in meters. And GPE is given in joules as usual. Okay, so those are the basic equations which you need to be aware of. And we'll go ahead and practice these in the quiz now. So let's have a go. Okay, so just one question in this quiz this time. We have a 10 centimeter spring compressed to a height of 8 centimeters and a ball attached to the end. We then release the spring and fire the ball upwards. We want to find out what is the speed of the ball when it's fired upwards, and also what's the maximum height that the ball does reach. And so basically we want to use the equations that we worked out in the first part of the video to try to answer this question. So pause the video and have a go. Okay, welcome back. Let's go through it. So the first thing we want to do is work out the elastic potential energy. And so remember, the elastic potential energy is half multiplied by K multiplied by E squared. And we are given K over here. K is 4 newtons per centimeter. And so because our extension is also going to be in centimeters, we don't need to convert anything in this case. Now to work out our extension, we know that the original unstretched length of the spring was 10 centimeters. We compressed it to a height of 8 centimeters, and that means our extension is 2 centimeters, or if you like, you can say it's minus 2 centimeters because you compressed it. Because we're squaring it anyway, it doesn't really matter what you put. So we can calculate this now as half multiplied by K as 4 multiplied by the 2 squared, or the minus 2 squared. It won't make a difference. Okay, so you can use that to work out your elastic potential energy in the spring in the first place. So you should get a total of 8 joules of elastic potential energy. And the key thing here is, in this system, the energy can be transferred, but we have this concept of conservation of energy. So whatever energy we start off with is the energy we're going to have at the end. So the next part of the question, then we want to work out the speed of the ball when it's fired upwards. Well, we know that the equation for kinetic energy does involve speed. And so over here, I can write the equation for kinetic energy is equal to a half multiplied by the mass multiplied by the speed squared. And what we can say is that when the spring reaches its unstretched length, there's no longer any extension, and therefore we know that the elastic potential energy has now gone to zero. At its unstretched length is when the ball is going to be released, so we can work out what the velocity or the speed of the ball will be when it's fired upwards. So we can say that 8 joules of the elastic potential energy was entirely converted to the kinetic energy, and that becomes half multiplied by the mass, which we don't have, which we'll actually do need to have. So we'll, yeah, sorry, you wouldn't have been able to solve this completely, but you should still have been able to get an answer in terms of m, but we'll just say m is 1 kilo to make it easy. So half times by 1 times by h, half times by 1 times by v squared, and v squared we don't know, and so we can rearrange this to get the speed, and so the speed is going to be 8 divided by a half, or multiplied by 2, divided by 1, and square rooted. Okay, so we just rearrange that for the speed, and so you should get 16, square root of 16 is going to be equal to 4 meters per second. And so that's the first part, that's part A. What is the speed of the ball when it's fired upwards? It's going to be 4 meters per second. Next, we want to find out what is the maximum height that the ball reaches, and for this we're going to assume that the zero height is going to be set when the spring is at its unstretched length. So what we can say here is that all of the kinetic energy, or all of the energy at the beginning, was converted to gravitational potential energy, because at its maximum height, essentially what's happened is, at this stage, all of your original energy has been converted to gravitational potential energy, and that's the only energy you have left. So initially, we've gone through this transfer of elastic potential energy being transferred to kinetic energy, and that kinetic energy is now going to be transferred to gravitational potential energy. So you start off with 8 joules of elastic potential energy, that's converted to 8 joules of kinetic energy, which is then going to be converted to 8 joules of gravitational potential energy. So once again, we can write that our equation is mass multiplied by g multiplied by h, and we can say that 8 joules is equal to the mass, which was 1, multiplied by g, which is 9.8, multiplied by the height. So now we just need to rearrange for the height. That's what we're trying to find out. And so we just get 8 over 9.8 should equal your height. And if you put that into your calculator, you should get approximately 0.8 meters. Okay, so hopefully you got that right. Apologies, I didn't put the mass, but you might have got it in terms of m instead. But therefore, that's an example of energy being transferred. We've used all the equations that we needed to use previously, and we can see how the energy is transferred from each step. So hopefully that makes sense, and I'll see you in the next one.